have a look at page 23. Okay, have a look at page 23. This one is a good exercise on seeing what I'm trying to talk about. This one is March 2017 P42. Okay, so look at question 6. All right, so here, if you look at part 6a, state a similarity and a difference between electric field lines and gravitational field lines around an isolated positively charged metal sphere. Okay, so in your case, you are supposed to make a comparison between gravitational field and electric field here for isolated positively charged metal sphere. Okay, so because it's a metal sphere, obviously it has mass. It's made of metal, it obviously has mass. Therefore, there is gravitational field. So you want to look at how the field lines would look like for electric and gravitational field for this particular sphere. Because it's positively charged and it's a sphere, we already went through the discussion, it should be similar to a point charge. So your field lines would look like this. Okay, this is for your isolated positive charge. Okay, maybe I just draw it as a sphere. If I draw it as a sphere itself, this is how it looks like. No? Okay, it will still be a radial line, but the direction will be that is pointing outwards, following the direction of force on a positive test charge. But if I consider the gravitational field around this sphere, this one is mass around this sphere, your field lines again will be radial. Okay, because it must be akin to that of a point charge. But your direction of your gravitational field will be directed inwards. Okay, because it follows the direction of force acting on a test mass placed inside that field. For electric field, place a positive test charge. This is the direction of your electric force on the positive test charge. This will be the direction of your electric field. But for a gravitational field, you place a test mass. The direction of your gravitational force on your test mass is the direction of your gravitational field. Okay, so this is basically your E field. This is actually your gravitational field. Okay, so what are the differences and what are the similarities between both of them? The first similarity that you can say for both of them is that the field lines are radial. Okay, or you could also kind of say this: there's greater separation of lines with increased distance from the center. They're actually referring to the part where the further you go away from the center of the sphere, the greater your separation. Something like this. You can see that your separation is increasing, right? The further away you go from the center of the sphere. This is another way of saying that lines are radial, actually. But what is the difference between the two fields? The difference is that gravitational field lines are always directed towards the sphere, whereas for electric field is always directed away from the sphere. Okay, so this is the similarity and the difference here. Okay, so this one is pretty straightforward. Now, if you then move your attention to B, you have a positive point charge Q that's positioned at a fixed point X, and an identical positive point charge that is positioned at fixed point Y, as shown in the figure below. So this one is your charge X with positive Q. This is also your charge Y, also with positive Q. Then after that, they tell you that the charges are separated in a vacuum by a distance of 10 centimeter. This is the separation between them. And they mentioned that points A and B are on the line XY. Point A is a distance of 2.5 centimeter from X, and point B is also a distance of 2.5 centimeter from Y. The electric field strength at point A is 4.1 times 10 power minus 5 volt per meter. Calculate what is charge Q here. Okay, what is this charge positive Q here? That's what the question wants you to find out. What is the charge positive Q here? So this one will relate to what we've just mentioned just now. They specifically told you that the electric field strength at point A is this one. This is the resulting electric field strength at point A due to charge X and charge Q. Sorry, this is the resulting electric field strength due to charge X and charge Y. Okay. So if I want to find out the magnitude here, just like I mentioned to you, you always try to place a positive test charge to test the field at that point. So if you consider the effects due to charge X, what do you suppose is the direction of your electric field due to charge X? It would be towards the right, isn't it? Following the direction of force on a positive test charge. This one will be the direction of your field strength due to X. Then how about if you consider the direction of the electric field strength due to Y? Okay, so it again follows the direction of force acting on a positive test charge. So this is positive, this is positive. Your electric force obviously will be towards the left. Likewise, your field strength would be towards the left too. So your EY will be towards the left. Okay. So from here, if you then want to find out what is the electric field strength at A, you can easily say that EA is actually EX plus with negative EY. Okay. This is what we are having now. Okay. So your EA is equals to EX minus EY. From there, you go and expand out the equation. It should be 1 over 4 pi epsilon naught Q over Rx squared minus 1 over 4 pi epsilon naught Q over Ry squared. Your Qx is actually just positive Q. Your Qy is also just positive Q. Okay, that's why you don't see me writing X and Y here. It's because I already sub in the X. It's because I already sub in as Q itself. Okay, now when it comes to your Rx and Ry, this 2.5 centimeter is your Rx, the distance between the main charge and your test charge. But when it comes to your Ry, I draw at the top so that it's easier to see. Your Ry is actually this one, the distance between your main charge and your test charge. This one is actually your Ry, which by right would be 10 centimeter minus 2.5. Okay, so this one is 7.5 centimeter. Okay, so you have all those values there. All you just need to do now is to sub those values in. So because you're having the same charge Q, you can factorize the Q out, then divide by 4 pi epsilon naught. After that, you get this 1 over Rx squared minus 1 over Ry squared. Then from there, subsequently, you can try to find out what is your Q. The main thing to find here is your Q, isn't it? All the other values are actually known. You know Rx, you know Ry, you know EA. So what's left for you is really just to sub in the values. EA is 4.1 times 10 power minus 5. Then Q 4 divided by 4 pi divided by epsilon naught 8.85 times 10 power minus 12. Sub in the value of your Rx. Don't forget to square. submit the value of your ry. Again, don't forget to square. Eventually, you will be getting your answer as Q equals to 3.21 times 10 power minus 18 coulomb. That is what you will get in your current case. Okay. So this is the basic workings of it. You may be able to rewrite it in an easier way, okay? But this is how I wrote it at that time, okay? So your answer will be 3.21 times 10 power minus 18 coulomb. So that is for this particular part. Then after that, if you move on to the next page, so here they then mention to you on figure 6.2, sketch the variation of the electric field strength E with distance D from A to B along line AB. Okay. So in your case here, they want you to sketch the variation of field strength with distance D from line AB. So what they want is for you to sketch E with D. Your D is measured from A to B. Okay, if you read the question carefully, they say your D is defined from A to B. This is how your D is going to be measured. It's starting from A. So at this point here, EA itself was already mentioned to you as 4.1 times 10 power minus 5, right? Okay. So your graph will start at that value. But what do you think will happen as you go a bit further? You will obviously be getting an E net of equals to 0. Because remember just now at this point here, we already went through how it was derived. EA is actually EX plus with negative EY, right? Yeah. So you can imagine what happens when your D increases. When D increases, let's consider what happens to the field strengths due to X and Y. Rx would be increasing such that the field strength due to X decreases, while at the same time, Ry would be decreasing such that the field strength due to Y increases. So right now, you can actually say that as D increases, Ex continues to drop while Ey continues to increase. Now, from what we did earlier, we consider Ex to be positive while Ey to be negative. So the conclusion that you can get from this is that your E net becomes less and less from positive to negative. If you were to draw out the graph of resultant field strength with distance between the 2 points, this is what you expect to see. If your y-axis is your resultant field strength and your x-axis is the distance measured from point X, let's assume that this point is point X itself and this point is point Y. So the variation of field strength with distance is going to look something like this. There will be a point where your field strength is going to be 0. But which point is it going to be 0 exactly? If you look back at the diagram, point X and point Y have the exact same magnitude of charge. So you can expect some sort of symmetry here. So because of that symmetry, the point where your E net is going to be 0 would be exactly in the middle between the 2 points. So if right now the distance between the 2 points is actually 10 centimeter, the point where your E net is going to be 0 will be at 5 centimeter. Okay, but the graph inside your question doesn't want you to plot from point X. They want you to plot it specifically from point A. That is where your distance D was measured in the first place. They want you to plot it from point A all the way to point B. Okay, And the distance between point A and point B, if you again look at the diagram, is actually going to be 10 minus 5 centimeter, giving you 5 centimeter. Okay, so you want to plot it some point away from point X, specifically 2.5 centimeter away from point X. So you are going to start drawing your graph somewhere around here. Okay, 2.5 centimeter away. And then after that, you end at point B, which is also 2.5 centimeter away from point Y. So if you can see from here that here to here is 5 centimeter, point B is 2.5 centimeter away from point Y, it's going to be somewhere here. This one is 2.5 centimeter away. This one is point B. And then point A was also 2.5 centimeter away, but it's from point X. So the graph that you want to plot right now in your question is actually this particular part here. Okay. It should cover only 5 centimeter length in total from A to B, and it will be having an E net equals to 0 right exactly in the middle. In other words, it should be 2.5 centimeter here and also 2.5 centimeter here. As for the magnitude of your field strength, your question did mention that the field strength at point A is 4.1 times 10 power minus negative 5. So what you would have at point A right over here is going to be 4.1 times 10 power minus negative 5. And then when you're talking about point B, because of the symmetry that you see, it's going to be having the same magnitude too, just that it's going to be negative. So this is your graph that you want. So from this diagram here, this one is basically the same thing as before. I just want to highlight to you certain things. Just now I wrote it in the previous diagram. This is where your E net is equals to 0 because EX equals to EY. Okay? Because that time I mentioned to you, if you consider placing a positive test charge here, and then you have your, maybe I just try and redraw it here for you. Wait now, just give me some time here. This one is A, it's a positive charge. This one here is B, it's also a positive charge. So somewhere in the middle, you place a positive test charge here. Sorry, this one is X and Y. Okay, I'll just put this as X and Y first now. Okay, just put this as X and Y. If I put a positive test charge here, EX will be towards the right, EY will be towards the left. So that my E net or EP or EA or whatever would just be EX plus with negative EY. Okay, so right at the center here, E net is 0 because EX equals to EY. But right at this region here, this one is where I told you that your E net will be towards the right because EX more than EY. And then for your case here, this one, I mentioned to you your E net will be in the opposite direction because EY is now more than your EX. Okay, that was the understanding here. So now the question is really just asking you, you have a small positive test charge placed at A. You place your small positive test charge here now. The electric field strength causes this charge to move from rest along line AB, okay, along this line here. All right. So describe the acceleration of the charge as it moves from A to B. Okay. So consider this one of the things that I did mention to you was that field strength is Fe over Q, right? So Fe is actually QE. Now, if your Q is constant, that would mean that electric force is proportional to your field strength. Okay? Electric force is proportional to your field strength. Okay? And then after that, another thing that you can also say is this. For the case of a charge that's placed inside an electric field, your F net is actually your electric force. If you're trying to relate force with acceleration, you always use F net equals to ma, right? For the case of electric field, your F net is your Fe. So Fe is equals to ma. Now, if I tell you m is constant, doesn't this mean that Fe is proportional to A? Okay, so there's a relation between these two that you can kind of make now. You can actually say that E is proportional to A. Okay, so with that in mind, the first thing you could say is that your acceleration of your charge is going to be proportional to your electric field strength. So what this means is this. If your E drops, your acceleration obviously drops. If your E increase, your acceleration obviously will increase, right? So consider this now. When you're moving from here to here, your E is dropping, isn't it? So your acceleration will be dropping. So as it moves from A to B, your acceleration will decrease, but it will be decreasing to 0 all the way to midpoint here. Okay, but after that, what happens? If you keep on moving from here to here, your E net will actually start to increase, but in opposite direction. But right, it's supposed to, you can say it's decreasing, but you can also say that it's increasing in opposite direction, right? So your A is increasing in opposite direction. That's why here you can say that then the acceleration increases in the opposite direction. Okay, so there's one thing that you can actually see from here. If I have a test charge that is between this region here now, my E net, my direction of motion is here. This is my direction of motion. But my direction of my electric force is also going to be in the same direction. This one, I will actually speed out. But then once I reach this point here, for my positive test charge, my motion is here, still going towards the right, but my Fe suddenly becomes 0. This one, you actually stop accelerating. You have actually reached max speed. Okay, from here to here, from this for this region here, because your net force is still towards the right and your motion is towards the right, your force and your motion are in the same direction, you will obviously speed up. But once you reach this point here, right in the center, you are still moving towards the right, but your electric force has actually dropped. So you do not have any acceleration anymore. But before this, you were speeding up, right? So if you were speeding up before this and then you suddenly stop accelerating, obviously you will reach maximum speed here. Okay. Then after that, what happens after that? After you've gone past that point? After you've gone past that point, you are now, say, probably here. Yeah, I try to draw it here. Your motion is still towards the right, but your electric force is now opposite direction. Your Fe net is now in the opposite direction. So since your motion and electric force are in opposite direction, this one you actually slow down. Okay. So that's just one thing to note here. for the first half of your motion, you actually speed up. Then after that, you reach a point where E net is 0, F net is 0. That is where you reach max speed. Then after that point, you start to slow down. Okay. So that's another way you can interpret your diagram here. Okay. Now, if you just look at page 66 of your worksheet, under page 66, you have a question asking you what is meant by a field of force, the lesson. You can just say that a field of force is a region where a particle experiences a force, okay? In my answer here, I say it's a region of space where a particle experiences a force. You don't really need to write the phrase of space here. Whatever phrase that you see inside a round bracket in my answers, usually those are optional to be written in following the convention inside your marking scheme. In your marking scheme, anything that is inside a round bracket, those are actually not required to be written inside your answers. Only the ones that are usually underlined are the ones that would be required inside the marking scheme. All right. So if that is okay, then you move on to part 2. State a similarity and the difference between the electric field due to a point charge and the gravitational field due to a point mass. So if you're talking about a point charge, for example, this one here, say is your point charge, is positively charged. The field line around this point charge here would be radial. It seems to be coming out from one point. Okay, so let me just draw this nicely here for you. It will be radial like this. Okay, and there's a certain direction associated with them. For a positive point charge, the field direction will be pointing outwards because it's always following the direction of force acting on a positive test charge placed at that point. Say, for example, if I place a positive test charge here, because this is positive, you are going to experience some sort of repulsion. This positive test charge here will experience an electric force outwards. So therefore, your electric field direction or your field direction itself is actually just going to be outwards. Okay, this is for isolated positive charge. In the case that you have an isolated negative charge, it's going to be the same thing too, just that your field direction is going to be in the opposite direction. So if I try to draw your field lines here, it again will be radial, like this. Okay, but the direction will be pointing inwards. Because if you consider a positive test charge that is actually placed at that point, any point inside your electric field, say I place a negative test charge right over, sorry, a positive test charge over here. Okay, I place a positive test charge over here. Because the two charges involved now is positive and negative, you're going to have attractive forces. So the force acting on your positive test charge is actually going to be inwards towards the main charge itself. So therefore, the direction of your electric field would be inwards. Okay, so this is for point charge. But when you're talking about point mass, in your case, if it's a point mass or it's just a point with a mass, you would have something like this again. It again will be having a radial field line like this. But the direction is fixed to always be inwards. Because the convention is that for gravitational field, the direction of your field is determined by the direction of force acting on a mass placed inside the field. So if I put a test mass here, masses will always exert attractive gravitational forces on each other. So your gravitational force is always going to be inwards. So since it's inwards, your field direction must be inwards. Okay. So what is a similarity that you can see between your point charge and your point mass? Is this. Your field lines are always radial. Okay, both field lines are radial. Okay, and there are different answers that you can also say. You could say that both actually have an inverse square variation. When it comes to the electric field strength for isolated point charges, you will always use E is equals to 1 over 4 pi epsilon naught Q over R squared. You see, if everything else remains constant, E is actually inversely proportional to R squared. Whereas for a point mass, the gravitational field strength is G equals to Gm over R squared. Again, if everything else remains constant, G is actually inversely proportional to R squared. So you could say that your field strength or the field itself actually has an inverse square variation. Inverse because you see it's 1 over something. Square because there's a square term. Okay, they have inverse square variation. Or you could also say that their field strength tends to decrease with distance, because it was mentioned to you before that spacing of your field lines is a measure of your field strength. If you were to go further out from the center of your mass or the center of your charge, you will notice that the spacing is actually increasing from here to here. So here you see spacing increase with distance, your field strength will decrease for electric field. The same could also be said for your gravitational field. If you go further outwards, notice that the separation between your field lines is getting larger and larger. So again, your spacing is increasing, so your gravitational field strength is decreasing. So that's why you can say it decreases with distance. All right. But what is the difference here between your point charge and your point mass is that the direction is different. Gravitational field will always be towards the mass itself. There's no other direction. It must always be inside. But for electric field, it can be towards or away from the charge, depending on the charge itself, depending on the sign of the charge, more specifically. All right. It depends on the sign of the charge. If it's positive, it will be outwards. If it's negative, it will be inwards. All right. So this is just for this part. Then after that, if you look at part B, let me erase whatever you have here. So for part B, they mentioned that you have an isolated solid metal sphere of radius 0.15 meters situated inside a vacuum as illustrated. The field strength at the surface of the sphere is 84 volts per meter. Okay, so find out what is the charge Q on the sphere. All right, find out the charge Q on the sphere. They are asking you to find out what is this charge here. This is your main charge Q. All right, so you want to find out what's the charge Q here. And they give you one particular information. The field strength at the surface of your sphere is 84 volts per meter. Meaning to say, if you look at this surface here, your field strength is actually 84 volts per meter. So with this, you can actually now find out what is Q. All right. You can use this equation here. E is equals to 1 over 4 pi epsilon naught Q over R square. This R here isn't really referring to the radius. A lot of people tend to mistake that. This R here is actually the distance between the charge and the point considered. Okay, so your R here is really this one. When you want to use E equals to 1 over 4 pi epsilon naught, this is your R, which incidentally is the radius of the sphere lah. All right, so here you use that equation. E is equals to 1 over 4 pi epsilon naught Q over R square. Your field strength is 84. Your 1 over 4 pi epsilon naught, you can actually get it from the second page of your data sheet. It's actually the second page of your exam question actually. Your 1 over 4 pi epsilon naught is given as this. They also give you epsilon naught itself, but it will be easier to use this straight away lah. So if you use that straight away, you're going to get 8.99 times 10 power 9 Q over R square. Your R square is actually 0.15 meter. Don't forget to square it. You will now get Q equals to 2.1 times 10 power minus 10 coulomb. All right. So this is pretty straightforward. Then you move on to the next page. Let me just get rid of this thing here. Okay, so if you now move on to the next page, they mentioned to you also to find the electric field strength at point P, a distance of x 0.45 meter from the center of the sphere itself. Okay, so they want you to find out the field strength at a new point, which is at this point. Let's just call this E2 lah. All right. Previously, they already told you what was the field strength at the surface of the sphere, which is say E1, 84 volts per meter. So this one is E1 equals to 84 volts per meter. So they want you to find out the new value of E2. Given that you already found out your main charge here as 2.1 times 10 power minus 10 coulomb. Okay. This is already the main charge already found for you. So if you now want to find what is E2, you have two ways to go about it. Either you just use back the original equation, E equals to 1 over 4 pi epsilon naught Q over R squared, which in turn will give you this. Your 1 over 4 pi epsilon naught is 8.99 times 10 power 9. Your main charge is 2.1 times 10 power minus 10. Your separation square now is actually 0.45 squared. Okay, because here they kind of mentioned to you that P is actually 0.45 meter away from your charge. This one is actually your new R. Okay, it's the distance between your charge and the point considered. So if you sub that in, you will eventually get your answer as 9.32 volts per meter. Okay, now there's another different method also that you can use. This one is by using ratio. This one for some people it may be more tedious. If you consider these 2 points, E1 and E2, whatever field strength you want to find at those 2 points, they are always going to be related by this equation. Okay, so you know this equation relates to both points. You want to find the ratio between them. You need to first identify what is constant for both of those cases in this equation. This one is constant. Is a constant in itself. The Q, the main charge for both cases, is also constant. So you can say that in your case, E would actually be inversely proportional to R squared. Okay, let me just show you the working. Here I say that E is equals to 1 over 4 pi epsilon naught Q over R squared. Because Q is constant here, E is inversely proportional to R squared. So I can say E2 to E1 is R1 squared to R2 squared. All right. Therefore, E2 over 84 equals to 0.15 squared to 0.45 squared, giving you 9.33 volts per meter. Okay. So this one, let me just rewrite this. If I say it as this one is actually me saying E2 to E1 equals to 1 over R2 squared to 1 over R1 squared. That's how I got this. All right. So you have that one should be okay. Just use whichever method that you feel is easier for you. Okay, now in part C, they mentioned to you that you're supposed to use the information from B to show on the axis of this figure below the variation of your electric field strength with distance x from the center of the sphere for values of x from 0 to 0.45 meter. So what you had was a sphere, charge sphere Q. Okay, and then after that, you're considering the electric field strength with distance x from the center of your sphere. Okay, now because this one is a uniform sphere, charged uniform sphere, because this is a charged uniform sphere, because of the fact that it's a uniform sphere in itself, we can actually say this one is identical to a point charge. Okay, so when it's identical to a point charge, we can use this equation. E is equals to 1 over 4 pi epsilon naught Q over R squared. The E equals to 1 over 4 pi epsilon naught Q over R squared is only for point charges. Okay. Earlier in the lesson before, I did mention to you that if you're talking about the electric force, Fe equals to 1 over 4 pi epsilon naught QQ over R squared. I mentioned specifically this one was only for point charges, right? When it comes to your electric field strength, it's also the same thing because your electric field strength came from Fe divided by Q. The Fe that you use to get this one was for between point charges. Therefore, whatever equation you have here must also be for point charges only. Okay, so for your case, because you know that this is a uniform sphere is therefore identical to a point charge, you can now use this particular equation. All right. So as mentioned to you before, Q was constant. This would mean that E is inversely proportional to R squared. If you were to try to plot a graph of, say, field strength versus distance, or field strength versus R versus separation, E versus R, you will get a graph that looks like this. It's a exponential decay curve. All right. So this is something that you would have learned from maths. It's going to be an exponential decay curve. But when you look at your graph that is inside your question right now, notice that they give you values on the axis itself. So you cannot just simply draw the curve. You need to follow certain values. You need to indicate certain points on your curve. The easiest one would be to use back what you have found from your question, because they already mentioned this to you, see. Use information from B, which is what you have above, to plot the graph. So from the part B that you did before, when your x1 was 0.15 meter, your E1 was 84 volts per meter. When your x2 is 0.45 meter, your E2 is 9.3 volts per meter. So you have to indicate it inside your graph now. You need to have 0.15 at 84. You need to have 0.45 at 9.3. Okay, this one is 84 volts per meter. This is 9.3 volts per meter. So you have these 2 points. You just draw this curve, okay, exponential decay curve, because it's following this relation. All right. But there's another thing to note for here. What about the case before your 0.15 meter? The question is asking you to draw from 0 to 0.45. So we started off at 0.15, right? What about what is inside here? Okay. So at distances below 0.15, this is actually inside the sphere already. Okay. Above 0.15, this is already outside your sphere. Okay. Now, one of the things that you should know specifically when it comes to charged uniform sphere is that the field strength inside the sphere is always going to be 0. Okay, there's another line that you're supposed to draw here, which is this one. Okay, so you're supposed to remember that field strength is always going to be 0 inside a charged uniform sphere. Okay, if you are inside the sphere, the field strength is always going to be 0. So you need to draw this other line too. Okay, and then you just draw another line joining the first 2 lines. This one here. Okay, this is actually your complete line. The first line in red, the second line in orange, the third line in green. This is how it's supposed to be. Okay, field strength will be 0 inside the sphere, but outside the sphere, it will follow this relation. E is inversely proportional to R squared. Okay, this is how you get your graph shape. Now, as to why is it that we say that field strength is always going to be 0 inside your charged uniform sphere, some of your past year questions will actually ask you to explain why is the field strength inside a charged uniform sphere 0 in the first place. For this, you actually need to refer to page 15 of your electric field notes. Okay, this part here was actually explaining to you certain characteristics of charged uniform sphere. All right. So you just look at the point that is highlighted in green here. I already did mention to you within the sphere itself, any distances less than your radius, your field strength is always going to be 0. Okay. Now, electric potential remaining constant here, this one we'll leave it for another time. Just focus on the part where they tell you that field strength is 0. So you will be required to explain why is field strength inside a charged uniform sphere 0. The explanation is actually under these bullet points below here. Okay. Now you need to consider this one first. When you're talking about charged uniform sphere, because they carry charges, that must mean that they are made out of metal. Okay, you cannot have a charged plastic sphere or anything like that, right? So if you have a charged sphere, it really kind of implies to you that it's made out of metal. So when it's made out of metal, metals have free charge carriers. That's how it's able to conduct electricity in the first place. So now the idea is that when you're talking about a charged uniform sphere, your free charge carriers inside the sphere are actually free to move about initially. Okay, you look at the sphere, you have free charge carriers, they are actually initially free to move about. Okay, but the thing is that your charge carriers normally carry the same sign of charge. It could be all positive, it could be all negative. All right, say for the sake of our discussion is all positive now. Because they all carry the same sign of charge and they're free to move about in the first place, they actually will tend to repel themselves as far away as possible. You will never have a case that the charge carriers try to move close to each other. They will actually try to move far away from each other. So because they repel and they can move, they will now move as far away as possible and they'll actually go towards the surface of your sphere. Okay, that's the max they can go. That's the furthest they can go away from each other. All right. So after that, they cannot move anymore, right? So while at the surface, they will tend to still repel each other until such a point that they stop moving. Okay. Generally, we will say that they tend to distribute themselves uniformly over the surface of the sphere until they can no longer move. They've achieved something like equilibrium here. Okay. So because they can no longer move at the surface, there is actually no resultant electric force acting on the charges anymore. Okay, because what you would have understand from AS is that in order for something to move, you must have resultant force. Okay, so if they don't move, that would have mean that there is no resultant force acting on them. So here you say that because they no longer move, there's no resulting electric force. And from there, you can then conclude that your field strength is 0. Now, how do you come to this conclusion is from this equation. Because you remember field strength is defined as electric force acting per unit positive test charge. If you already say that your electric force is 0, your electric field strength is going to be 0. Okay, that's how they conclude that. This particular point here is the one that will come out inside your exam. They will ask you to explain why field strength is 0 inside your sphere. Okay, so that's the reason in the first place why you have this graph shape. Why is it 0 inside your sphere? Okay, so that is okay. Then I move on to your next question.